Savannasaurus. Savannasaurus is a genus of titanosaurian sauropod dinosaur from the late Cretaceous Winton Formation of Queensland, Australia. It contains one species, Savannasaurus Eliatorum, named in 2016 by Stephen Poropat and colleagues. The holotype and only known specimen, originally nicknamed Wade, is the most complete specimen of an Australian sauropod, and is held at the Australian Age of Dinosaurs Museum. Dinosaurs known from contemporary rocks include its close relative Diamantinasaurus and the theropod Australovenator. Associated teeth suggest that Australovenator may have fed on the holotype specimen. At 15 meters, 49 feet, long, Savannasaurus was a medium-sized titanosaur. It is notable for its wide hips, which would have been over 1.1 meters, 3 feet 7 in, wide at their widest points. This would have distributed its body weight more evenly, along with a robust humerus, upper arm bones, and possibly also the tall astragalus, ankle bone. Combined with a flexible vertebral column, these traits would have made Savannasaurus better at navigating the muddy ground of the floodplains that it lived on. Other titanosaur lineages also show some of these traits, which might have been independently acquired from similar environmental pressures. Various traits suggest that Savannasaurus was an early diverging, or basal, member of the Titanosauria, but not a member of the more specialized group Lithostrotia. Among these are the absence of hyposphin hypantrum articulations in its vertebrae, which was one of the flexibility-enhancing traits that may have appeared in multiple titanosaur lineages. Paleobiogeographic analyses suggest that the ancestors of Savannasaurus and Diamantinasaurus were from either Asia or one of the southern Gondwanan continents. Regardless, they likely migrated to Australia through Antarctica around 105 to 100 million years ago. Discovery and naming. In March 2005, the first specimen of Savannasaurus was discovered by David Elliott, founder of Australian Age of Dinosaurs, AODF, along with his wife Judy and their children. The specimen, now catalogued as ODF 660, was found on the Belmont Sheep Station, 60 kilometers, 37 miles, northeast of Winton, Queensland. The site was given the number ODF 82, and is informally called the Ho-Hum site. Excavations by the Queensland Museum and hundreds of volunteers unearthed the specimen in July and September of that year. A siltstone concretion containing the specimen was split along gypsum-filled fractures using jackhammers and chisels, with the pieces being marked to facilitate reassembly. Preparation of the specimen took around a decade, with their scribes and microjacks being used. Adhesives, such as superglue and araldite, were then used to put the pieces back together. The marks allowed the orientation of the specimen as it was found to be reconstructed, which informed a three-dimensional site map constructed with photogrammetry. ODF 660 consists of around 40 bones, 1 cervical, neck, the 3rd through 10th dorsal, trunk, at least 4 sacral, hip, and at least 5 caudal, tail, vertebrae, cervical and, fragmentary, dorsal ribs, portions of the shoulder girdle, including a fragmentary scapula, a left coracoid, and both sternal plates, parts of the forelimbs, including portions of both humeri, a fragmentary ulna, the left radius, and hand bones, the left 1st to 5th metacarpals, the right 4th metacarpal, and 2 phalanges, the fused hip bones, namely both the left and the right pubis and ischium, foot bones, the left astragalus and right 3rd metatarsal, and other fragments. One of the foot bones was originally thought to have belonged to a theropod, while the metacarpals were initially also interpreted as having come from the opposite hands. The specimen is the most complete sauropod specimen known from Australia, and represents approximately 20% to 25% of the animal. The bones were preserved over an area of less than 20 square meters, 220 square feet. While the dorsal vertebrae were not articulated, they were preserved in sequence in front of the hip bones, allowing for their identification. The ribs on the left side appear to have been crushed prior to fossilization, before all of them were fragmented further. The 5th dorsal vertebra and both humeri show signs of being trampled by other dinosaurs before fossilization, which may also explain the scattered bones. However, the bones were less scattered than other dinosaur specimens from contemporary rocks. A third excavation in September 2006 discovered no additional remains, but a partial centrum from a caudal vertebra was found on the surface in 2013. Having been nicknamed Wade, ODF 660 was formally described and named in 2016 by Stephen Poropat and colleagues in a paper that also described a skull belonging to Diamantinasaurus. They identified ODF 660 as the holotype of a new genus and species, Savannasaurus Eliatorum, the generic name of Savannasaurus, from Savannah, the root of the word savanna, refers to the environment in which it was found. While the specific name Elliottorum honors the Elliot family and their contributions to Australian paleontology, the preliminary anatomical description of OTF 660 in this paper was supplemented in 2020 by another paper from many of the same authors, which provided a full description of its osteology. Description: Savannasaurus was a medium-sized titanosaur that measured about 15 meters, 49 feet, in length, with a weight of around 20 tons, 22 short tons, and a shoulder height of around 3 meters, 9.8 feet. Vertebral column. As with most other members of the titanosauriforms, the vertebrae of Savannasaurus were camellate, or pneumatized by small holes created by air sacs, and they lacked hyposphen hypantrum articulations that allowed neighboring vertebrae to interlock. The cervical and dorsal vertebrae of Savannasaurus were all episocylous, or having a centrum, vertebral body, that is convex in front and concave behind. All other members of Sauropoda have episocylous cervicals, and all other members of Macronaria have episocylous dorsals. Unusually, the front articulating surface of one of the caudal centra was undulating, being concave in the upper half and convex in the lower half. Poropat and colleagues suggested this as a distinguishing characteristic of Savannasaurus. The other caudals were amphicoelous, or having centra that are concave on both ends, which was also rare among titanosaurs save for Bay Oceanmensaurus and Angiosperms. The only known cervical vertebra of Savannasaurus is considered to have come from the rear of the neck due to its proportions. Unlike most titanosaurs but similar to the ancestral, plesiomorphic, condition among sauropods, the vertebra had a subtle keel running longitudinally along its bottom surface. Mendozasaurus, Ovirosaurus, Austroposeidon, and Raptosaurus also have such keels. There was a well-developed longitudinal fossa, or excavation, along the side of the vertebra that extends for nearly its entire length, unlike in many titanosaurs where it was faint or absent altogether. In contrast to more specialized titanosaurs like the Saltosauridae, the parapophysis, one of the rib articulations, was restricted to the front half of the centrum. Associated cervical rib fragments suggested that they were relatively long, extending for the length of at least 3 centra. Like many titanosaurs, the articulating surfaces of the dorsal centra in Savannasaurus were shorter vertically than they were wide. The dorsals had weakly developed ridges bordering the sides of their bottom faces, as in Diamantinasaurus and Episocoelicaudia, where they were better developed, but Savannasaurus lacks the keel on the bottom of the centra as in these species. Like most other members of the Symphospondyli, the sides of the centra bore teardrop-shaped pneumatic holes. The articular processes at the front of the centra known as the presygapophyses were connected by a sheet of bone, lamina, the transpresygapophyseal lamina, in the front dorsals. This sheet was V-shaped as in most titanosaurs, but it was basically flat in the rear dorsals unlike most other titanosaurs. Notably, the laminae in the dorsals of Savannasaurus were bilaterally asymmetric. The left side of the vertebrae would have been better reinforced by extra laminae. Also, unlike Episocoelicaudia, the dorsal neural spines on top of the centra increased in height towards the rear dorsals, were not split into two, and were taller than their corresponding articular surfaces. In addition to the undulating articulating surface in one of the front caudal centra, caudal A, the two front caudals, caudals A and B, of Savannasaurus have another distinguishing characteristic. Like the non-titanosaur Symphospondyle and Padilosaurus, the front caudal centra had shallow pneumatic excavations on the sides surrounding small holes, whereas most members of the Symphospondyli have only the holes and not the excavations. This characteristic had previously been regarded as a distinguishing characteristic of the non-Symphospondyl and Brachiosaurids. Two other caudal vertebrae, caudals C and D, are known from further back in the tail. The centra of caudals B, C, and D were about the same length, suggesting that centrum length did not vary considerably. However, both articulating surfaces were wider than tall in caudal C, while the front one was taller than wide in caudal D, suggesting that it was further forward than caudal D. Like other titanosauriforms, the processes that enclosed the neural canal, the pedicles, in caudals C and D were 2/3 the length of the centra, and were shifted forwards relative to the midline. Shoulders and forelimbs. Two distinguishing characteristics of Savannasaurus are found in the sternal plates. First, they were D-shaped with straight outer margins when viewed from the bottom, instead of being kidney-shaped as in other titanosaurs. Second, they lacked the long ridges that were present on the bottom surfaces among most members of Sauropoda. In general, the bottom surfaces were devoid of the grooves and pits on the top surfaces which are indicative of cartilage coverings. However, like most other titanosaurs, the sternal plates would have been at least 65% as long as the humeri. In Savannasaurus, The ratio was approximately 71%. The coracoid of Savannasaurus was oval-shaped in side view, unlike the characteristically quadrangular coracoids of Saltosaurids, and the glenoid fossa on it, which articulated with the humerus, was much larger than that of Diamantinasaurus. Unlike most titanosaur forms save for Daxiotitan, Ligabuosaurus, and Sauroposeidon, the articulation with the scapula at the back of the bone was taller than the entire bone was long front to back. Like Diamantinasaurus, Episocelicodia, and Saltosaurids, the humerus of Savannasaurus was robust. The radius was twisted about its axis, with the long axes of the two ends being oriented in different planes, seen otherwise only in Huabesaurus, Epacthosaurus, and Raptosaurus. The maximum width of its top end, 33% of the bone's length, and the presence of a strong ridge at the rear outer corner, the interosseous ridge, were more typical. Like all neosauropods, the hand digits of Savannasaurus were arranged like a horseshoe. Like Diamantinasaurus and Winton, the third metacarpals were the longest, followed by the second, first, fourth, and fifth. The third metacarpal was 49% the length of the radius, which was short for a titanosaur, but was at least 45% as in all macronarians. A distinguishing feature is that the bottom of the fourth metacarpal was hourglass-shaped, not trapezoidal or hexagonal. In life, the metacarpals would have been bound at the top and splayed at the bottom. The presence of phalanges is unusual. All titanosaurs but Savannasaurus and Diamantinasaurus had hands formed only by metacarpals. All digits but the first likely had phalanges, although their articulating surfaces on the bottoms of the metacarpals did not extend to the front as would be expected. Pelvis and hindlimbs. The most distinctive feature of Savannasaurus was the width of its pelvis. Its sacrum was 1.07 meters, 3 feet 6 in, wide, and its fused ischium pubis complex was at least 1.14 meters, 3 feet 9 in, wide. Its sternal plates were around 85 centimeters, 2 feet 9 in, wide to accommodate this. Although titanosaurs were wide-bodied in general, these proportions made Savannasaurus extremely wide-hipped, surpassed only by Episocelicodia and Saltosaurines such as Nuconsaurus. Other pelvic proportions in Savannasaurus were also unusual. The ischium's articulation on the pubis was 56% as high as the bone was long, higher than most titanosaurs. The ischium in Savannasaurus was relatively short, being 63% as long as the pubis. It was at least 70% as long in all other titanosaurs but Raptosaurus, 54%, and Episocelicodia, 64%. A characteristic that distinguished Savannasaurus from every other sauropod is that the front-to-back length of the ischium was only 42% of the bone's width. On the ischium, the iliac peduncle, one of the processes surrounding the acetabulum, hip joint, was only 32% of the bone's length, lower than most other sauropods. Furthermore, the front end of the ischium was 49% as wide as the bone was long. Only Diamantinasaurus had a similarly high ratio, 51%. Another distinguishing characteristic of Savannasaurus is the presence of a subtle ridge that separates the front upper portion of the pubis from the rear plate. The ridge is parallel to another ridge just below the opening known as the obturator foramen. This latter ridge corresponds to multiple ridges in Diamantinasaurus. Also like Diamantinasaurus, there was an expanded boot at the tip of the pubis. On the ischium, the ridge at the back which separated it from the pubis extended further to the side than Diamantinasaurus, but less so than Winton. Further below, in the ankle, the height of the astragalus was greater than its diameters either front to back or side to side, which is unusual among titanosaur forms. Two unusually low ratios in the astragalus are distinguishing features. The side-to-side diameter was 87% of the height, and the side-to-side diameter was 98% of the front-to-back diameter. Unlike Diamantinasaurus, there was no shelf on the astragalus below where it would have articulated with the fibula. Classification. For their 2016 description, Poropat and colleagues conducted a phylogenetic analysis to test the affinities of Savannasaurus and the new skull specimen of Diamantinasaurus. They added these specimens to a dataset created by Philip Mannion, one of the co-authors of the description of Savannasaurus, and colleagues for the 2013 redescription of Lusotitan. The analysis placed Savannasaurus and Diamantinasaurus together in a clade, unified group, close to the root of Titanosauria, outside the derived, specialized, group Lithostrotia. Similar results were recovered by Rafael Royo Torres and colleagues in their 2017 description of Sauriotitan, Mannion and colleagues in their 2017 description of Bauivria, Alexander Avryanov and Vladimir Efimov in their 2018 description of Volgotitan, Bernardo Gonzalez Riga and colleagues in their 2018 redescription of Mendozasaurus, and Pedro Mocho and colleagues in their 2019 descriptions of an indeterminate Lithostrosian and Oceanotitan. In 2020, Poropat and colleagues noted a number of features that support a position for Savannasaurus outside Lithostrosia: the horizontal transpresygopophysial laminae, the lack of constriction in the vertebrae of the sacrum, the amphicoelous caudal centra, the pneumatic excavations on the front caudals, the D-shaped sternal plates, the presence of phalanges, and the lack of a longitudinal ridge on the side of the pubis. At the same time, the lack of hyposphin-hypantrum articulations in the dorsal and caudal vertebrae provides evidence against a more basal, non-specialized or rootward position, given their presence in many non-titanosaur titanosauriforms and rarity among titanosaurs. Some titanosaurs also had these articulations. The basal Antisaurus and the Lithostrosian Epacthosaurus had them in the dorsals, while the Lithostrosians Epacthosaurus, Apizocelicodia, Vulgateton, and Malawisaurus had them in the caudals. However, Poropat and colleagues recognized the possibility that they could have been acquired independently multiple times among titanosaurs. Nevertheless, other phylogenetic analyses based on Mannion and colleagues' 2013 dataset have found different results. Royo Torres and colleagues repeated their 2017 analysis after removing a titanosauriform from the Cloverleaf Formation, Chubutasaurus, and Angolotitan. They found instead that Savannasaurus and Diamantinasaurus were successively basal to a clade consisting of Baeotian Mansaurus and Dongianasaurus. Savannasaurus shared amphicoelous caudal centra with both genera, various features of vertebral laminae with Baeotian Mansaurus, an unkeeled dorsal centra and the absent longitudinal ridge on the side of the pubis with Dongianasaurus. However, unlike Savannasaurus, Baeotian Mansaurus had hyposphin-hypantrum articulations, and both genera had bifidorsal neural spines, i.e., split into two. Similarly, for a 2019 paper naming the nucleate Colossosauria, Gonzalez Riga and colleagues extended their 2018 phylogenetic analysis and found an unresolved polytomy of Savannasaurus, Baeotian Mansaurus, Dongianasaurus, and a clade of more derived titanosaurs. Diamantinasaurus was placed in a more derived position as the sister group of Lithostrosia. Also in 2019, Julian Silva Jr. and colleagues extended the 2018 analysis of Gonzalez Riga and colleagues for their redescription of Uberabateton. They found Savannasaurus outside the Titanosauria in a polytomy with Euhelipus, Urkatu, Kiao and Long, a clade of Tangviasaurus and Puwayangosaurus, and more derived symphospondyles. They also found Diamantinasaurus and Baeotian Mansaurus to form a clade inside the Saltosauridae. Poropat and colleagues considered their results unusual in 2020. In their 2019 redescription of Jiangshanasaurus and Dongianasaurus, Mannion and colleagues found both Savannasaurus and Diamantinasaurus inside Saltosauridae by equally weighting characteristics in their dataset, but using implied weighting eliminated this result. The phylogenetic tree from the analysis of Poropat and colleagues in 2016 is reproduced below, at left, with emphasis on relevant glides. An alternative tree by Royo Torres and colleagues in 2017, from the analysis that removed the Cloverleaf Titanosauriform, Chubutasaurus, and Angolotitan, is also shown at right. Paleobiogeography. As the southern supercontinent of Gondwana broke up during the Cretaceous period, dinosaur faunas became more diverse. Conventional hypotheses suggest that the faunas from the Gondwanan continents, including Australia, would be closely related, but mid-Cretaceous Australian dinosaurs have been found to be more closely related to their Laurasian, northern, counterparts in spite of the fact that Laurasia and Gondwana had already been separated by the Tethys Ocean for a significant span of time. In 2016, Poropat and colleagues tested this hypothesis by performing a paleobiogeographic analysis using the results of their phylogenetic analysis. Using the modern geography of the continents, they found that the ancestors of the Australian sauropod Savannasaurus, Diamantinasaurus, and Winton were likely Asian. Incorporating Cretaceous geography suggested ancestral ranges also spanning the Gondwanan continents of South America, Africa, and Indo-Madagascar. Combining their paleobiogeographic analysis with time-calibrated phylogenies based on fossil age estimates, Poropat and colleagues inferred that some phospondylans and titanosaurs had attained a wide distribution across the world by the Barremian epoch, 131 to 125 million years ago, if not earlier. However, they ultimately diverged into a number of lineages ultimately with limited geographical ranges. They attributed this endemism to regional extinction events. They estimated that the Savannasaurus plus Diamantinasaurus and Winton lineages had separately reached Australia no later than the late Albian epoch, 105 to 100 million years ago. but the exact timing depended on the models that they used. The oldest Australian titanosauriforms, Ostrosaurus and the Huonton sauropod, date to this interval. Although they acknowledged the possibility of sampling biases, Poropat and colleagues considered a late Albian dispersal likely because of the most probable dispersal route, which would have entailed beginning from South America and crossing through Antarctica to southeastern Australia. In the Aptian to early Albian epochs, this region of Australia would have been situated at a latitude of 70 degrees south, with a cool, temperate climate. No sauropods have been found from these latitudes and environments, suggesting that they were adapted to warm climates and avoided these regions. Thus, they would likely have been unable to disperse across Antarctica until the late Albian, when global warming led to a smoother temperature gradient. Poropat and colleagues suggested that climate preferences could also explain the Laurasian affinities of Australian dinosaurs. In 2020, Taikubo applied network analysis to a phylogenetic supertree of Australian dinosaurs. He found a strong connection between Australian dinosaur faunas and other Gondwanan dinosaurs, and identified Gondwanan Cretaceous dinosaurs as a distinct community. Thus, he suggested that most previous results identifying affinities between Australian and Laurasian dinosaurs were caused by insufficient sampling of Gondwanan dinosaurs and the phylogenetic instability of Australian dinosaurs. For instance, he pointed out that the Megaraptor in Australovenator was thought to be an offshoot of an Asian lineage until more Gondwanan Megaraptorans were found. While he suggested that the same was true of these sauropods, he also recognized the possibility that they had a different biogeographical history than smaller dinosaurs. Paleobiology. Like all titanosaurs, Savannasaurus was likely a wide-gauge sauropod, meaning that it would have stood and walked with its feet far apart from the midline. In 2020, Poropat and colleagues pointed to the width of its sternal plates and sacrum as evidence for a wide-gauge stance. The robust humerus of Savannasaurus was also considered a likely adaptation to a wide-gauge stance, which would have been convergently acquired with saltosaurines. They also suggested that the unusual form of the astragalus was also an adaptation to weight-bearing, but the absence of other hindline bones made this unclear. Yet, Poropat and colleagues also noted traits that would have increased the flexibility of the vertebral column, namely the absence of hyposphin-hypantrum articulations and the presence of prominent excavations, the centropresygopophyseal fossae, below the transpresygopophyseal laminae. Both of these were shared with Diamantinasaurus, but were otherwise rare among sauropods. Poropat and colleagues noted that both Savannasaurus and Diamantinasaurus would have lived on a floodplain with clay-rich soil and high rainfall. See section Paleoecology, which would imply that the ground would occasionally become muddy and hazardous for large sauropods. They considered it possible that environmental pressures would have selected for individuals capable of navigating muddy ground, and that Savannasaurus might have spent more time near water than other sauropods. Flexible vertebrae, to escape bugs, barrel-like bodies similar to those of hippopotami, wide-gauge stance, and robust forelimbs, all to distribute its body weight, would all have been helpful for such a niche. They postulated that saltosaurines might have been subject to similar selective pressures, and so the typical titanosaur body plan may have been acquired convergently multiple times. While the same environment could also have selected for longer necks to provide easier access to water, Poropat and colleagues noted that Savannasaurus and Diamantinasaurus likely had relatively short necks, though overlapping cervical ribs might have improved stability in Savannasaurus. Paleo Environment. The Belmont Sheep Station is part of the fossil-bearing rock units in the Upper Winton Formation, which has been dated to around or just after the boundary between the Cenomanian and Turonian epochs of the Cretaceous, about 93.9 million years ago, based on uranium lead dating of detrital zircons. It is the geologically youngest rock unit of the Mesozoic era in the Eromanga Basin. 6 major facies, or distinct rock types, are found in the Winton Formation. 2 different types of sandstone-siltstone combinations, associated with meandering rivers, crevasse splays, and levees, mudstones, associated with oxbow lakes and ponds, sandy siltstones to silty mudstones, associated with tidal flats, plant-rich mudstone and coal, associated with swampy ground, interformational conglomerates, associated with flooding. These rocks suggest that Savannasaurus lived on a freshwater floodplain covered in broad, meandering river channels with low-energy water flow, which was subject to occasional flooding. During the Cenomanian and Turonian, the Winton area had a latitude of around 50 degrees south. Leaf fossils show that the climate was warm, with a mean annual temperature of 16 degrees Celsius, 61 degrees Fahrenheit, and wet, with a mean annual precipitation of over 1,300 millimeters, 51 in. Although the weather was seasonal, There was no extreme cycle between the wet season and dry season as is the case today. The growing season would have been 8 to 9 months long. However, weather patterns also appeared to have been cyclical on a multi-year basis, similar to the modern Pacific decadal oscillation. This may also have influenced the sporadic flooding. Conifers and Angiosperms were the most common plants in the Winton Formation. Conifers included the Cypress sequoia, the Araucaria anamoidea, and the Poticara protophylliclidoxylon, while Angiosperms included Lovelia and various unnamed forms. Other plants included the ferns Philotero and Tempskia, the liverwort margentites, the horsetail equisetites, the Benedictalian zotosamites and Ptilophyllum, and the Ginqualian ginkgo. Savannasaurus lived alongside a diverse vertebrate fauna in the Upper Winton Formation. Contemporary dinosaurs included the sauropods Diamantinasaurus matildae and Wintonotitaean wattsi, the Megaraptor and theropod Australovenator wintonensis, and indeterminate ankylosaurians and hypsilophodonts. A tooth belonging to Australovenator was found near the Savannasaurus holotype, suggesting that its feeding was responsible for the specimen's disarticulation. Other archosaurs included the pterosaur Pterodactylenonid and the crocodilian Isisfordia duncani, along with other undescribed pterosaurs and crocodilians. Additional vertebrates known from the Winton Formation are chelid turtles, an indeterminate varanoid lizard, the lungfish Metaceratodus elioti and M. wallistoni, and ray-finned fish including Cladocyclus gedesi. Invertebrates were dominated by the bivalves Alatheria jacquidi, Hierodelagundi windiensis, Megalovirgus windonensis, and Proeria mcmichaeli, but also included the gastropod melanoides, dragonflies, scorpionflies, and dorobodid mites known from trace fossils found in silicified wood.